Hello and welcome again to my Physics Online video lecture series. In today's video, I'm going to be talking about the magnetic force on a current carrying conductor. In other words, I'm going to be talking about if I have current passing through a conductor and it's interacting with a magnetic field, how much force is that magnetic field going to be applying to the current and hence to the conductor. So shorthand, we might say magnetic force on a current, etc. So to begin with this video, there's maybe a few little notes that we should recall. The first note is how does a magnetic field interact with a moving charge, or an individual moving charge, or a charge carrier that's in motion. And that force is simply given by the cross product of charge velocity with magnetic field, Q V cross B. Second thing that we need to recall is that current is basically consists of a bunch of moving charges. It's kind of rate at which charge passes through a given cross section per unit time, but for our purposes here, it basically means that we could envision current as just involving a whole bunch of moving charged particles. Thus, current I is dq dt, whether you want to use lowercase q or uppercase q, and that other point that I made was that we could think of current as just consisting of a bunch of moving charge. More properly, this is what is sometimes called carrier current, but we're just going to call it current in this video, since at this point you don't really know what to distinguish a carrier current from. So current is a bunch of moving charge carriers, which is the same thing as a bunch of moving charged particles. So with that as the background, we might write out the total charge on, let's say, a straight segment of wire that's carrying some current as FB is equal to QV cross B times number of charge carriers, which in turn is Q times V cross B times the density of charge carriers times the cross-section area of the wire times the length of the wire. So nothing especially weird has happened here yet. But now let's sort of combine terms a little bit, and you end up with Q. Remember that V is a dx by dt, or a dl by dt if you'd prefer, times NaL, all cross with B. And then note that NaL Q dx dt, this is collectively the same thing as a dq dt times L. And so we can write that the magnetic force is current times L cross B. And this is what you get if you're just looking at a nice straight section of wire. For what it's worth, oftentimes we will rearrange this a little bit to find the force per unit length in this section of wire. Another thing to note is that we've kind of done a little bit of moving around of what holds the vector term in all this. We went from a velocity to a length, and we did not use the current as a vector term. Current's usually a scalar quantity. So how do we determine the direction of L? Well, let's say that I happen to have a segment of wire like this that is carrying some current. So maybe the positive charges happen to all be moving this way in this segment of wire. Then we would say that in some sense the current is to the right, and if this right here is length L, then this right here would represent my vector L. So these are my charges moving to the right, positive charges. If they're negative charges, then they're moving to the left. So this is L, and then if I happen to have a magnetic field like so, this maybe is my B. This is sort of straight with respect to this magnetic field, B. And so if I have some angle here, theta, then the magnitude of this force is going to be whatever current I have times the length times B times the sine of this angle theta between the two. So that works out very well for a long straight wire. We could do a quick example for that. So in the example that we're actually going to work through, we are given a 2.0 meter segment of wire lying along the x-axis and carrying a current of 3 amps, which has been placed in a uniform magnetic field given by 1.0 I hat minus 2.5 j hat plus 4.0 k hat millitesla. We're trying to determine how much force, so this really means that what we're looking for is this quantity, the magnitude of the force. We're told that it's a 2.0 meter segment L, that being 2.0, lying along the x-axis. That basically means that L hat is plus or minus I hat. We don't actually have enough to specify whether it's plus or whether it's minus, but since we're trying to figure out a magnitude only, it actually doesn't matter whether the current is moving to the right or whether the plus charges are moving to the left. We are given a current, and of course like B is given here, so don't need anything further for that other than to note that this is equivalent to 1.0 I hat minus 2.5 j hat plus 4.0 k hat times 10 to the minus 3 in Tesla. So we got to convert to Tesla if we're going to find the force in newtons. So the force itself, FB, is going to be, and again, we don't know whether it's plus or minus. Let's just assume plus. That means that our force is going to be given by basically plus 3.0 amps times 2.0 meters I hat crossed with 1.0 I hat minus 2.5 j hat plus 4.0 k hat times 10 to the minus 3 Teslas. Now the basic rules of cross product are that I hat cross I hat is 0, I hat cross j hat is plus k hat, and k hat cross I hat is plus j hat, so I hat cross k hat is minus j hat. So basically what that means is that my actual force is going to be 6 times 2.5, so that is 15 negative, and that is k hat. And then 6 times 4 is 24, also negative, in the j hat direction times 10 to the minus 3 Tesla. Now what we care about is the magnitude, so the magnitude FB is basically the square root of the dot product of B with itself. And so that is going to be 10 to the minus 3 Teslas square root, basically negative 15 squared plus negative 24 squared. So we put all that into our calculator, and what we get is 28.3 times 10 to the minus 3 Tesla. And maybe I should note that the units here, this is Tesla meter amp, so those units convert to newtons. So this is about 28 millinewtons, or if you prefer, FB is about 2.8 times 10 to the minus 2 newtons. Either way, we have kind of our answer. So that's a quick example. Now, we're assuming so far that everything is sort of straight elements, or at least straight relative to the field. So at each point we have the same field magnitude and the same relative wire direction. What would happen if our wire was bendy like this, and maybe we have some magnetic field like so? For that matter, the magnetic field doesn't even have to be in the same direction for each point of the wire. What would we do? Let's again assume that our positive charges are moving in the more or less rightward direction. So what we would do is we would just take an element of this wire, and this element right here has length dl. The current should be the same at each point in the wire. So this has current I, it's an element dl. This is the magnetic field, and the total force acting on the wire, in this case we'd have a df, so you'd get a df out of this. In this case df happens to be up out of the screen towards you, so df should look like I times dl cross b. And note that b might be b of xyz, so b of whatever the position is. And so then that in turn means that the total force, if I want to get the total force on this wire, I have to do an integral of both sides. And so this will be an integral of I times dl cross b. And that's my force for the wire as a whole. Now remember that an integral is a fancy sum. So that means you can break up your wire into kind of convenient segments. Like maybe if I happen to have a wire that's like this, and then the next piece is like this, and then maybe the last piece is circular like this, then I might have one segment here, one segment here, and one segment here. And so these two segments might just be a simple I times L cross B, and then this one is integrated from some limits, and then we add the three together. And so many problems maybe look like that. This one probably actually would look like that as well, where we would sort of pick segments in which the integral is doable, or in which maybe we don't even need an integral. We would find the force on that segment, and then we'd add up all the forces together at the end to get the total. Let's now consider a second example This one is kind of wordy. So we got three sides of a square and then a semicircle that form a sort of closed loop wire. And each of the sides of that square are of the same length as the total diameter of the circle. So in some sense you could maybe call these 2 times the radius. This also is 2 times the radius of your circle. Your wire is carrying a current of 1.5 amps. It's been placed in a uniform magnetic field of 160 Gauss. Remember that a Gauss is 10 to the minus 4 Tesla. So this is 160 times 10 to the minus 4, which is 0.016 Tesla. And then this field is parallel to 2 of the square sides. And we want to find the force. So first thing we might want to do here is draw for ourselves a diagram. So the wire basically looks more or less like this. And we don't really care which side ends up having the semicircle. We just know that this is 2R. We know that this right here is 2R. And that has also defined these two sides. And our magnetic field, we've been told, is parallel to 2 of the sides of the wire. So basically you've got a magnetic field that looks more or less like this. So the question becomes, how much total force? Now we're going to actually kind of make use of both the equation that I've written here as well as this idea that integrals are also sums. I'm going to break this up into 4 segments. So I'm going to call this segment 1, segment 2, segment 3, and segment 4. And I probably, as part of my diagram, should also label a direction for the current. It doesn't really matter which direction the current goes, whether it's clockwise or counterclockwise. I'm going to draw it clockwise in this case. What that does is it defines for us the sort of direction of DL in each case. So we should be able to therefore go piecewise in this. And it's worth noting that piece 1, let's do like this, let's put it green, we'll say piece number 1, the field is pretty much uniform relative to the side. So piece 1, we could just say F1, I'm just going to label it as F1, F2, F3, F4. We understand that these are magnetic forces. F1 is I times L1 cross B. And looking at this, you can see that for side 1, the current will be sort of up along the screen. The magnetic field is to the right. And so by the right-hand rule, you'd point your index finger up along the screen, you'd point your middle finger basically along the magnetic field, so to the right. And when you do that, what you end up getting, current is up, magnetic field is to the right, you end up getting a force that's sort of into the screen. So if I'm going to label the force here for number 1, I guess I could do kind of a darker green. That force is into the screen. And so in terms of this cross product, what I basically would have is, in some sense, I times L, and then upward, maybe we'll call that the y hat direction or the j hat direction, cross with, and then the magnetic field is B times I hat. So j hat cross I hat should give me negative k hat. So this is just negative I L B k hat, or I should say L1 B k hat. And that is in turn negative 2 times I R B k hat. Remember that L1 is 2 times R, 2 times the radius. We can put in the numbers later. Let's actually kind of move on to number 2. So again, we have a uniform field and straight wire relative to direction. So this should look like I times L2 cross B. And so in terms of our sort of vectors here, this is I times L2, so we might as well just put the 2R in here. And then it's actually in the I hat direction now. Along here, the current is pointing to the right, so this is the I hat direction. We're crossing that with B times I hat. I hat cross I hat is 0. So we just have the 0 for side 2. Side 4 is actually going to give us the same result. So we'll just put and 4, because 4, everything in here is the same, but you have a negative I hat for the first part. A negative I hat cross I hat also is 0. So we're left with option, or side, 3. This one is not uniform, and so basically we have to do sort of like a DF3, and that should look like I times DL for side 3, of course, cross B. So now we ask, what is it that side 3 is doing as far as DL? Put differently, we expect DL to have some sort of a function that we can actually integrate along. And if we look in sort of a semicircle like so, here's my poorly drawn semicircle. At different points on the semicircle, we're going to have a different sort of local DL vector. So right here, my DL vector is like this. Right here, my DL vector is like this. Right here, my DL vector is like this. So these are different sort of DL vectors as I go around the circle. And you'll see that I don't always get the same angle between the magnetic field B and my DL vector. And you know that as a general rule, when you have a cross product, A cross B, that is going to have a magnitude of A times B times the sine of the angle between them. So I expect the magnitude of the force to be different here than here. And so I need some way to sort of convert all of that. And basically the way that you do that is, first you recognize that B and DL are always in the same plane. And so the vector that's perpendicular to the two is always going to be in the same direction. In fact, it's if we wanted to do just DL hat cross B hat, for any choice of DLs along here, what we end up getting is the positive k hat direction. So in other words, my force on this side, although the magnitude is different at each point, the direction remains the same. And so we're basically just looking at what's the magnitude here doing. And so basically, collectively what this is telling me is that DL cross B should look like DL times B times sine of whatever angles between them times the k hat direction. Okay, so I don't have to worry about is the direction different at each point in this wire. Alright, now the next step is that we've got to figure out what DL is in terms maybe of a sine theta. So we kind of expect this DL and this sine theta to somehow link up because theta is a variable here. It obviously changes. B does not change. And so I need DL to change into a d theta of some sort. So in order to do this conversion to figure out a value for theta, let's consider a sort of sector here. This has radius r. We'll call this angle theta. And then this guy right here comes out here. This whole length right here is sort of a dl. And so this angle right here is a d theta. Well, geometry tells us that this angle between the B field and the DL is also going to be a theta. So in other words, this angle and this angle have to be congruent with each other. So what does all that get for me? Well, I can see that my DL must be equal to an r d theta. So now I've converted my DL into a d theta. Hooray! I also need to get limits of integration. I notice that if it's straight up like this, the way I've defined theta, I would have a 0. And if it's straight down like this, I'd have 180 or pi. So in some sense I have 0 less than theta less than pi. Right, so if I put all these things together, what I have is that for this third side, the force must be the integral from 0 to pi of B times dl, so B times r d theta, sine theta. This means that if I'm wanting to solve for F3 in this case, that let's pull all the constants out. I would basically have I times B times R times k hat integrated from 0 to pi of sine theta d theta. Again, that's a fairly straightforward integral. What it gives me is negative I B R cosine theta k hat evaluated from 0 to pi. Cosine of 0 is 1, cosine of pi is minus 1, so that gives me a force 3 of basically negative I times B times R k hat times basically negative 1 minus cosine of 0, which is 1. And so this is negative 2. There's a minus sign here. That makes it a plus sign. I end up with 2 I B R k hat. So to finish the problem out, I basically just need to evaluate these two things. Although if I'm paying especially close attention, I notice that in part 1 For segment 1, I had negative 2i rb k hat, and for segment 2, I have positive 2i rb k hat. So I could evaluate with numbers, but if I add all of my forces together, I have F1, F2, F3, and F4. F2 was 0, F4 was 0. F1 was negative 2i br k hat. F3 was positive 2i br k hat. And so even without plugging in the numbers for I, B, and R, I can see that these two are going to cancel, and so my total force on this wire actually ends up being 0. And this actually is a kind of general result, which we'll come back to in the future. Namely, if you add up all the forces around the wire, and so this is sum of forces equals 0. This could also be written, of course, closed loop of df. That'll be 0, or closed loop of IL cross B. So you can write it any one of these ways, I dl cross B. Any one of these things is saying the same thing, that for a closed loop within a magnetic field with a uniform field, meaning same magnitude everywhere, same direction everywhere, the total force on that closed current carrying loop will be 0. And that again is something that we will actually come back to in a future lecture. But for now, that was just kind of an example that we're doing. And so hopefully you learned a bit from this video, from these two examples. And as always, thanks for watching.